These notes are going to be about molarity, which is the bulk of the calculations for this unit. So let's talk about this. As we talked about earlier, molarity is a measurement of concentration. So if you remember from back before, there's this idea between concentrated and dilute. So concentrated means you have more of whatever it is dissolved in whatever amount of volume. Dilute means you have less. So that's how we measure this. It's that ratio of the moles per volume. We typically measure this in moles per liter, which is molarity. That's the big M. Big M stands for molarity. Yeah, so molarity is also known as big M. So if you ever see this word, big M means molarity or molar, kind of like your teeth, but not really. So that's what this kind of thing is all talk is this whole section is all about is putting a number to it. So that way, if you pour out a solution and you know the volume, you know how many moles you've added. If you want to know how many moles you need, if you know how many moles you need, you know the concentration, you can figure out the volume that you should add. A lot of times in chemistry, we're dealing with solutions of a certain molarity instead of just measuring out grams. So in a lot of ways, we use this similarly to molar mass. When if we're concerned with measuring molarity of a known or milliliters of a known solution versus grams of a known substance or solid. So let's go ahead and do some of these problems. This is the definition of molarity. So the formula really is molarity equals moles over liters. That's kind of how you can think about this. I'll do these in two different ways. You can also think of this more as like, yeah, you know, it kind of works better as a skeleton in all honesty. Kind of depends how you want to think about it. But here, I'll write out the formula. Moles per liter. Okay, so this question is asking what is the molarity of a solution that has 3.6 moles of sugar in 450 milliliters. The fact that it's sugar doesn't actually matter. The only thing that matters is moles and the milliliters. So let's go ahead and do this. Really quick, this is also important now that I see it. 1,000 milliliters is equal to 1 liter. That's going to be really important for us. So what we're going to need to do is convert milliliters into liters. Just by knowing that 1,000 milliliters equals 1 liter, we've got approximately, it's 450, which is pretty close to 500 milliliters. So that's like half of a liter. So we can actually just convert this to 0.45 liters right off the bat. Okay. That's a quick and dirty way of doing it. If you actually want to go ahead and solve for it, what you can do is you can go 450 milliliters, throw together a little skeleton. 1,000 milliliters is equal to 1 liter. Milliliters cancel out and you get 0.45 liters. So if you can just do it in your head, groovy. If you want to do a quick skeleton off to the side to figure out your volume, that also works just fine. So now we just need to solve for this. So molarity is going to be equal to the moles divided by the liters. We have 3.6 moles. We have 0.45 liters. So we just need to do the math. Let me grab my calculator here. I was not ready for this, weirdly. Okay. So 3.6 divided by 0.45 is 8. That's going to be 8 moles per liter. You can also do 8 molar. So the big M means moles per liter. So these are all the same thing. Moles per liter, molarity, same thing. You can read this as moles per liter. You can read this as molarity. You can read it as moles per liter. It doesn't really matter. It's the same thing. Okay. So that tells us this is pretty concentrated. 8 moles in 1 liter is not, that's a significant amount. I think for sugar, the actual saturation point is probably higher than that. The saturation point is going to be an actual concentration. So maybe sugar's saturation point is like 16 molar or 32 molar, or, who knows what it is, but it means you can pack more sugar before it will stop dissolving. Okay. So yeah, that's kind of what we're talking about here. Let's try another one. Ooh, this one's a little bit more complicated. How many grams of salt do you need to make 1.5 liters of a 6.5 molar solution? This is the kind of question I have to solve all the time when I'm making solutions for the lab. So I need to actually physically make the solution. I have salt, and I need to add water and figure out how many grams of salt I'm going to need. So for this one, I want to try, let's do this in a slightly different way. Let's try solving this one in a pure skeleton method. We'll see if you like it. You could still solve for this. The main thing that we need to do is we need to solve for, maybe I'll do it two different ways. Let me think about that for a second, how I want to do this. Well, either way, when I see 6.5, the big M, I automatically think that means mole per liter. Okay, so that's an equality that we could use. I see liters, I see a concentration. I'm looking for grams of salt, but to get grams, I know that I'm going to need moles. If I have moles of salt, I can also solve for grams of salt pretty easily. So as long as we can get to moles of salt, then we can get to grams of salt. So maybe let's start there. So I'm going to try doing this way off to the side. Maybe I've got enough room for both methods. So we've got moles, molarity equals moles per liter. We're trying to solve for moles. So moles is equal to molarity times liters. Okay. So that's going to be 6.5 molarity times 1.5 liters. We can also think of this as moles per liter, and then you can see here how the liters will cancel out and you end up with moles. So that's going to be 6.5 times 1.5, which is like 8 or something. No, it's 9.75. So that's 9.75 moles. So that is how many moles of salt we need to make this amount, to make 1.5 liters, which is quite a lot, of a 6.5 molar solution, which is pretty concentrated. And that's sodium chloride. So now we just need to convert moles to grams. So this is a good time for a little skeleton. And we just need the molar mass of salt. So that's going to be 22.99 plus 35.45. It's going to be 58.44 grams per mole. Okay, so we're going to take 9.75 and divide it by 58.44, and that's going to equal 0.17 grams of sodium chloride, and that's our answer. Okay. So for this one, I kind of used a little bit of algebra and then kind of threw in a skeleton. Let's see. I don't have a lot of space on here to show you. You could also do it just purely as a skeleton. Maybe I'll kind of show you how to do it for this one a bit. Yeah, that's gonna be fun. Okay, so that's how to solve that. We did two things really. For the first one, we were solving for molarity. This one, we were really solving for moles, but we just have to convert it to grams. This next one, let's solve for volume. So we're trying to solve for volume here. You know what, this one, I think I'll have enough space. Okay, so once again, we've got our moles and we have our molarity. So molarity equals moles per liter. We're solving for liter. So to do this, we're gonna have to do a little bit of funky math here. We have to do a little bit more algebra, but when you end up doing it, sorry, I didn't talk you through that, but I divided each side by liters, or multiplied by each side by liters, and then divided each side by molarity. So liters is going to be equal to moles divided by molarity. So let's see how that plays out. The moles is 12.3 moles, and we're going to divide that by 0.75. But remember, that's moles per liter, which is why moles cancel out and you end up with liters as your unit, which is great because that's what we're solving for. So this is going to be 12.3 divided by 0.75, which is going to be like 15. 16.4. All right, I'm getting close there, y'all. 16.4 liters. So that is our answer. Another way to solve this, just so you know, if you're using more of a skeleton method, which is my personal preference, because I don't have to think about this in terms of formulas, is I have a number and this is my equality. Because I remember this is moles per liter, right? So I would start with 12.3 moles. And then I would just insert the equality in whichever direction I need to. So in this case, I need moles on the bottom. So that's going to be 0.75 moles per 1 liter. And moles cancel out. And I end up with liters, which is what I want. 12.3 divided by 0.75 also equals 16.4 liters. So either way, you get the same answer. Okay. Awesome. So there's a whole bunch of packet problems that will go through this, but these are 3 examples of how to do this. Let's talk a little bit about concentration of ions in solution. So this is the, let me see, grams. Yep, that all works. Okay, just making sure I did that right. If you flip the page over or here, we talk about ionic and covalent solutions. This is very much like the electrolyte thing. So the idea here is that something that's ionic will dissolve into its constituent ions, but something that's covalent all sticks together. They both dissolve. There's just kind of a difference between those. And if you are dealing with an ionic solvent or ionic solution, you can talk about the concentration of ions, not just the concentration of the solution itself. So let's take a look at this sodium sulfate example. So sodium sulfate is a solid, and when it dissolves, it's going to dissolve into sodium ions and sulfate ions. For every 1 sulfate ion, you're going to produce 2 sodium ions because of that 2 right there. So what is the concentration of sodium ions and sulfate ions in 70 milliliters of a 2 molar solution? So let's look at sulfate first. Oh yeah, by the way, these little brackets represent concentration. So let me go back and write that. You might see these brackets, and if you ever see these, that means concentration in molarity. It's all the same thing. Okay. So this means concentration of sulfate ions. So let's solve for that. So we have the volume and we have the molarity. Yeah. So actually, in this particular case, the volume literally means nothing because we're only looking for concentration. We have been given the concentration of sodium sulfate. So what we're really doing here is it's more like, this is more like a molar ratio thing. So we have the concentration of the sodium sulfate and we need to find the concentration of the sulfate by itself. So the concentration of the sodium sulfate is 2 molar. And you can kind of treat these like moles. Like molar and molar kind of mean the same thing. The actual number of moles don't matter because it's a solution. So for every 1 mole or 1 molar of sodium sulfate you have, the concentration, oops, oh, well, this will work, it's fine. For every 1 molar of sodium sulfate you have, you're going to have the same concentration of sulfate ions. So this also ends up being that sodium sulfate has a concentration of 2.0 molar of sulfate ions. But what about sodium? Sodium ions, the concentration. We know that our concentration of sodium sulfate is 2.0 molar. I'm gonna get the lights back on. This is driving me crazy. It gets all reflective on the ink and I don't love it, especially while the ink is still kind of wet. Okay. So the concentration of the sodium sulfate is 2.0 molar, but for every 1 molar or 1 mole or molar of sodium sulfate you have, you're gonna have 2 of sodium. So this is really just a molar ratio. So in this particular case, your concentration of sodium ions is going to be double. Okay. I don't anticipate this coming up very often for you all, but it is something that you might expect to see. And especially for AP Chem, it's a good thing to kind of keep in mind how when things dissolve, the concentration of ions can be different. You'll have twice as much sodium as you do sulfate in any solution that you produce. Okay, I think there's one last thing that we should talk about. We're definitely not going to talk about dilutions, but we should talk about making solutions. So making solutions is, it's kind of like a whole procedure. And so what you want to think about for here is if you were to physically make this, you want to think about how you would measure this out. So barium nitrate is a solid. It looks the same as salt pretty much, maybe more like bath salts. Magnesium sulfate probably looks a little bit more like that. Otherwise, it might be a very fine white powder. I don't remember. So to make this solution, we're actually going to need to do some calculations and we can write out a procedure. We need to be able to measure a solid of barium nitrate in order to make the solution. So I think the first thing that we need to do is figure out how many grams of barium nitrate we're going to need. So this is a good time to do a little bit of math. So we want 500 milliliters of this solution. Let's convert that to liters. Watch out, we just did. Okay, great. Now it's in liters. And we know we want it to be 2.5 molar. That's moles per liter. So that's going to be 2.5 moles of barium nitrate per 1 liter. So that cancels out liters. So now we've got moles. Now we need to figure out the molar mass of barium nitrate so we can get grams. So 1 mole of barium nitrate is how many grams? Well, let's do some quick math here. Let's see, we've got 2 nitrogens, 6 oxygens. So let's see, 14.01 times 2 plus 16 times 6. Oops. Yep. Plus 1 barium, which is over here, and that's 1, oh gosh, you guys can't even see that, 137.33. I think that's going to be most of the mass. Okay, so 261.35. So 261.35 grams. So of barium nitrate. So let's take that number and multiply it by 2.5 and also multiply it by 500 and divide it by 1,000. And we get 300. Making sure that makes sense. Yep, that does. 326.69 grams of barium nitrate. Oof, that's a lot, but it makes sense. Okay, so just to review what I did here. I did this all in skeleton form. What I knew was that I know that barium nitrate, or this molarity, is moles per liter, which is a type of equality that I could use in a skeleton. I know that I'm trying to solve for moles. So as long as I put moles over liter and multiply it by some sort of volume, it's going to work. I use the skeleton to do a lot of conversions. So I really identified this as my starting value and that this is like my equality. So I started with the starting value, converted it into liters so that I could then convert it into moles and then converted moles into grams because I know I'm going to need grams for this procedure. So really what we need to do here is we need to add 326.69 grams of barium nitrate to 500 milliliters. Like that's the process. That's how you would physically make this. So we're going to first measure 326.69 grams of barium nitrate. We're going to add to a 500 milliliter flask. We're going to fill with water. And stir to dissolve. Okay, I didn't have this completely ready, but maybe in class, I will kind of walk you through this whole procedure. And I think we're going to do a lab for this one as well. I wouldn't be shocked. But making solutions is really, it's really pretty easy. The actual math is just knowing how many grams and how much water to add, and then you just mix them together. Fill with water, and let's say this should be distilled distilled water. Okay. So you might see a problem like this that crops up. So I just wanted you to be prepared for that. All right. So there's a whole bunch of math for you. I think it's going to take a little while to process this. So let me show you the work that will help you to do that. You're going to be working on pages 7, 8, and 9, I believe. Let me just double check. Maybe 10 as well. Yeah, 10 as well. So lots of practice, 7, 8, 9, and 10. Let's walk through them all real quick. Let me adjust the camera so we can maybe see that a little bit better. All right, I want to go through a few of these problems with you. I think I've chosen 4 on page 7, and then maybe we'll go through others in class as we go along. Okay, so the first question is, what is the molarity of a 0.3 liter solution containing 0.5 moles of NaCl? I don't care what it's made of, doesn't matter to me. All I need to know is I need molarity, so I need moles per liter. So that's going to be 0.50 moles divided by 0.3 liters. So that's going to be 0.5 divided by 0.3, and that's going to be 1.67 molarity, big M. That's our answer. That's it. Okay, so let's try another one. Number 4, how many moles of sodium chloride? Again, as long as I see moles and molarity, I don't really care what it is. Doesn't matter to me. Are present in 600 milliliters of a 1.55 molar solution. So the molarity I know is moles per liter, which is my equality. So let's start with the 600 milliliters. Let's convert it to liters. And we want moles, so we need moles on top. The number that you get with molarity is always the moles, and it's always per 1 liter. So the milliliters and the liters cancel out. We're left with moles. So that's going to be 600 divided by 1,000, which is 0.6, times 1.55. And that's 0.93 moles. And that's our answer. Okay. Let's try another one. How many liters of a solution are needed to make 1.66 molar that contain 2.11 moles of the fact that it's potassium permanganate? Don't actually care. As long as I've got moles, cool. If it had grams, I would need to know what compound it is, but it's just moles. So who knows? Who cares? So I'm going to do the same thing. This is my equality. This is 1.66 moles per 1 liter. And this is my starting number. Again, if you want to think of this more as an equation, that's fine. I just kind of think this is nice. So in this case, I need to put 1.66 moles on the bottom and 1 liter on the top because I'm solving for liters and canceling out moles. So that's going to be 2.11 divided by 1.66. And that, in this case, is going to be 1.27 liters. And that's my answer. Wow. Algebra. This is honestly, it's like exactly the same as molar mass. It really is. It's just instead of molar mass, we're using molarity, but mathematically and conceptually, it is identical. Moles per volume instead of like grams per mole. But really, it's the exact same concept. Okay, let's do one more. What is the molarity of a 6.5 milliliter solution containing, okay, grams? As soon as I see molarity, sorry, that's what we're looking for. As soon as I see grams, I do actually care what this is. It actually now really matters to me. We did one very similar to this in the in the notes. So let's do this other one. How many grams of calcium hydroxide are needed to produce 500 milliliters of a 1.66 molar calcium hydroxide solution? So let's actually do this one instead. So I need grams. The information I've been given is volume, and I've also been given this moles per liter. So that's 1.66 moles per 1 liter. That's the information. So let's start with the volume. Let's figure out moles, and then we can convert moles to grams. So let's do it in that order. So let's do 500 milliliters 1,000 milliliters is 1 liter. 1.66 moles per 1 liter. So boop, 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 those all cancel. And now we just need the molar mass of calcium hydroxide. So let's figure that out. Let's see, we're gonna have 2 oxygens, that's 16 times 2 plus 2.02, because that's hydrogen is 1.01, but times 2. I just like to do that math in my head for some reason. And then calcium is 40.08. If you need to review molar mass, we should definitely talk about that and definitely ask me for help. Otherwise, you can go back and rewatch some of those videos. They're still up. So 74.1 grams per mole. Okay, so now we just do the math. So 500 divided by 1,000, I'm just going to say that's 0.5 because that's easy, times 1.66 times the 74.1 is 61.50. And that is going to be grams because those moles cancel out. That's our answer. Et voila. Pretty cool. Okay, there's lots of practice. This is going to take you some time to get used to, I think. So this first page should be a little bit more straightforward. Page 8. Just taking a quick look to see if I see anything weird. You know, I'm seeing about the same thing. I'm seeing a lot of grams in this one. So this is going to be a good one to include molar mass with. Page 9, I'm also seeing, yeah, a lot of grams. But a few things like here, how many moles? So that's not too bad. Yeah, but again, very similar kinds of problems. And then page 10, yep, I'm seeing a lot of stuff with grams. You're gonna have to convert from grams to moles. That's good, good practice. Number 8 originally asked for molecules, but I've decided not to deal with that. So just solve for moles here. We'll make it a little bit more simple. And number 9 is one of these step-by-step procedures. So we might need to talk more about this one, but that's the one, that's why I took these little notes here real quick for you. And I'll have to walk through a real demo with you, which I just wasn't prepared for right now, but we'll do it for sure. Of making a solution of the whole procedure. But really the most important thing is understanding to make a solution, you need a certain mass of something solid and water, and you just mix them together. But the question is how much water and how much solid. And there is kind of a finicky way of the procedure for doing so, but it's not super important. Okay, I think that's plenty of practice and plenty of talk about molarity for right now. Give them a go and see if you can come up with the right answers. And if you can, that's great. If not, we'll work on it together. And I think the next section will be on, oh, you know what? Making Solutions was supposed to be its own video. Oh, well, I guess it's in this one. So we'll figure that one out. No big deal. We'll talk about dilutions, which is another really big part of this unit. So thanks, everyone, and go give that a try.